Hi and welcome back. Today we're going to talk about linear relationships that occur between independent and dependent variables, both measured at the interval or ratio level of measurement. Let's begin. So we're going to talk about linear prediction generally. We'll look at the building blocks, covariance and standard deviation. We're going to calculate Pearson's R and R squared. We'll go through an example. We'll walk through all the calculations discussing statistical significance, degree, and form with bivariate regression. We'll build it as a predictive model, graph the relationship. All right, so let's start. Imagine that we were trying to predict the George W. Bush feeling thermometer in 2008 from how people felt about the Democratic Party on a feeling thermometer. Now, these feeling thermometers go from 0 to 100, and they're measured in degrees. And you can see from this image here that there's a certain amount of dispersion of the dots. And you can remember back to middle school where each of these dots would represent an x and y coordinate. So they represent a place on both the x-axis and the y-axis. And you can imagine that if we drew a line that minimized the amount of distance simultaneously through all the dots, we might get a line that looks like this. You can see the downward trend, and you can see that the dots don't perfectly line up on the line. So generally speaking, when we do linear prediction, we use the bivariate regression model, which can be written as y hat equals alpha plus xb plus epsilon, where y hat equals the estimated value of the dependent variable. That's the line that we're looking at. Alpha equals the intercept of the prediction line. That would be the value of y, or in this case, the value of our dependent variable, the George W. Bush feeling thermometer, when x equals 0. So you can imagine if x is 0, what would be our guess as to the feeling thermometer score for George W. Bush? The role that x plays in this equation, that's the vector of x's. That's all the values of our independent variable. B is the slope of the line, and perhaps you remember back to when you first took coordinate geometry, you get rise over run for your slope. So a unit change in x producing how much of a change in y. Or for each degree warmer that someone feels about the Democratic Party, how does that change our prediction as to how people would feel about George W. Bush? And finally, epsilon, because everything prior to the plus epsilon in this equation refers to the line. Epsilon refers to the dispersion around the line, because the line doesn't perfectly predict all of our points in this scatter plot diagram. So you could imagine here that the generalized version of this formula, y hat equals alpha plus xb plus epsilon, can be thought of in this case as the estimated value of the Bush thermometer is going to equal the intercept plus the Democratic thermometer times the slope plus epsilon. And of course the line itself is just being predicted as Bush thermometer equals intercept plus Democratic thermometer times slope. So the building blocks that we're going to use to help us understand this relationship is based on the idea of covariance. And we'll also want to think about the standard deviation of x and y. So you can think of covariance as the long-run simultaneous average of the misses about the respective means of x and y. So for example, if you took a point here, any point, and you said, okay, how far does it miss both the mean of x and the mean of y? And we can get a calculation for that. So the covariance formula in the numerator, you can see it's x minus x bar times y minus y bar divided by n minus 1. And we're going to look at standard deviation as well. And you can visualize if all these dots here lined up on either the x-axis or the y-axis, we would be thinking about the dispersion of one variable. And that variable, of course, has its own mean and its own standard deviation. Okay, so when we calculate Pearson's R, the way that Pearson's R is calculated is by dividing covariance by the standard deviation of x multiplied by the standard deviation of y. It's relatively straightforward to calculate, but we'll get to that in a second. And that's going to give us R. And you can think of R, or Pearson's product moment correlation coefficient, or Pearson's R some people might call for short, as being a measure of association. It's going to produce a correlation coefficient. So it will range in value between 0 and 1, positive or negative. And so that'll give us a sense of both the directionality of the relationship and the strength of the relationship. Now, the correlation coefficient is good in and of itself in giving us both direction and strength of the relationship, but we can do even more. We can square the value of R, and we get R squared, which is relatively simple to calculate. It's just R squared. But the interpretation of r squared is very intuitive. It tells us the proportion of the variation in the dependent variable that can be explained when we know the values of the independent variable. So r squared is a very powerful predictor for us. And you can see that to get this model, we're also going to need other formulas to help us understand. So r squared will tell us how much the model explains. B is going to be the slope of the line, and we're going to get that from working with our sum of squares shared between x and y divided by our sum of squares for x. We'll get alpha as equaling the mean of y minus b times the mean of x, and then we'll work on getting statistical significance using the t statistic for r. Okay, so let's start by predicting student GPA from the number of absences that a student has. And we can have a hypothesis, you might imagine. The more absences that a student has, the lower we'll observe their GPA to be. And of course, a null hypothesis might be something like a student's GPA is unrelated to the number of absences they have. So we're going to go through a variety of steps. We're going to calculate standard deviation for x, standard deviation for y, covariance of x and y, Pearson's r squared. We're going to calculate b, alpha. We'll draw a plot, and we'll calculate t. We'll make a claim about statistical significance. It doesn't have to be done necessarily in this order. Of course, the earlier ones do. So, of course, to calculate standard deviations, we need means, etc. So let's take a look at the setup. This is not at all unlike the setup for calculating a variance. And you can imagine this vector of y's that we have, this vector of x's that we have, and then all the columns that follow. So the first two columns would be just your typical columns when calculating variance for x. Your next two columns would be exactly the same thing, but calculating variance for a y. And then our final column is where we have our x minus x bar times our y minus y bar, which will be the product of the following two columns, the x minus x bar and the y minus y bar. So if we were to start calculating, you could see that once we've calculated, you sum all the xi's, divide by the number of observations, and get the mean of x, and we can see that the mean number of absences given our sample is 3.5. And we do the same thing for y. The mean grade point average of the 3.5, 3.2, 3.6, etc., that is going to sum to 17.1 divided by 6 will give us 2.85. So with these two means, we can now calculate the x minus x bar and y minus y bar columns. So for example, you can see here in the column where we're looking at the x's, where x is 0, if we subtract x bar, so 0 minus 3.5 is going to give us negative 3.5, and when we square it, it gives us 12.25. And we're going to continue that pattern until we've done all the x's. So when x equals 6, we're going to subtract our 3.5, our mean, and that'll give us 2.5. When squared is 6.25. When you have all of your x minus x bars calculated, sum that column, and that will give us the sum of squared error for x, which in this case is 37.5. Then repeat the process for just the y's. So we have where y is 3.5, and y bar is 2.85. 3.5 minus 2.85 is 0.65. When squared is 0.4225, etc. All the way down to 1.6 as a GPA. Minus 2.85 is negative 1.25. When squared is 1.5625. Sum them all. That gives us a sum of squared errors for y of 2.815. Finally, let's get a sum of squared errors for x and y shared. So we'll take our x minus x bar column and multiply it by our y minus y bar column. So in the case where we had an x of 0 and a y of 3.5, we had x minus x bar was negative 3.5, y minus y bar was 0.65, and the product of the two is negative 2.275. We'll do that all the way to the last observation where we had an x of 6 and a y of 1.6. And when we sum the x minus x bar times the y minus y bar, that 2.25 times negative 1.25, that gives us a negative 3.125. Let's sum this final column, the product of the x minus x bars times the y minus y bars, and that'll give us a sum of squared errors shared between x and y of negative 8.75. Perfect. So now we have our sum of squared errors for x, our sum of squared errors for y, and our sum of squared errors shared between x and y. Oh, and by the way, while we're here, because we have a mean of x and a mean of y, we have a special coordinate point that we're going to use later. The point where the mean of y intersects with the mean of x is what's called the centroid. And we could just remember that in coordinate geometry points. So it would be where x is 3.5, comma y equals 2.85, and we would illustrate it this way. So 3.5, comma 2.85. That's the centroid. Now, the reason why the centroid is so important is any line that's going to pass through all the dots, or as close as possible to all the dots, by definition must pass through the mean of both x and y. So that's going to be one of the points that'll help us plot our line. The other point in this line that we're going to know at some point will be the intercept, and we're going to get that in a little bit. Okay, so let's move forward. Okay, so now that we have the sum of squared errors, we can get the standard deviation of x and the standard deviation of y. We've already calculated the sum of squared errors, so we can just divide them by n minus 1 and take their square root. So the standard deviation for x is 2.7386. Same thing for y. We're going to divide by 5 and take the square root. Will give us a standard deviation for y of 0.7503. And finally, we can get the covariance shared between x and y. We have our sum of squared errors shared between x and y of negative 8.75. We're going to divide by n minus 1, 5. So that gives us a covariance of negative 1.75. Now, together with the standard deviation of x, the standard deviation of y, and the covariance, we can now get Pearson's R. So let's go ahead and calculate Pearson's R. So let's put it in the formula. So negative 1.75 divided by, right, that was our covariance, divided by the standard deviation of x, 2.73, times the standard deviation of y, 0.75. That gives us an R of negative 0.8516. Now, what that's telling us is two things. When we have an R, remember, it's a correlation coefficient, and you can interpret it like any other correlation coefficient, like a gamma or a tau b or what have you. And so the closer you get to 1, at absolute value of 1, positive or negative, the closer you're getting to perfect prediction. So if you're getting close to negative 1, you're getting close to negative prediction, i.e. as values of the independent variable are increasing, values of the dependent variable are decreasing. And you get a positive coefficient if as values of your independent variable are increasing, the values of your dependent variable are also increasing. So in our case here, we have a negative 0.8516. That means we have an extremely strong relationship between the number of absences and the grade point average of the student. Now, conceptually, we might be getting worrisomely high with this kind of a correlation coefficient. We're getting awfully close to 1, and we worry about problems of instrumentation. We worry about issues where the closer we get to 1 in a positive or negative direction, the more likely it is that we're measuring the same thing. So you have to ask yourself philosophically, is absences the same thing as grade point average? Now, in this case, I'm going to say no, because unless your grade is entirely based upon your attendance, they're probably separate features. Okay, so let's continue. So we have R. We know it's a negative relationship. We know it's a very strong relationship with that negative 0.85. And when we square the value, we get R squared. And in this case, we get an R squared of 0.7253. Now, that's telling us something else very interesting. It's telling us, this is a proportion now, 72.5% of the variation in the dependent variable, grade point average, can be explained when we know the values of the independent variable, absences. It's telling us that there's a lot of the variation in someone's grades that are being explained just by the number of absences, 72.5%. Now, we can use our calculation table that we set up to also determine the slope and the intercept. You can see that the slope formula uses the sum of squared errors shared between x and y divided by the sum of squared errors for x. So we've already calculated those, so we can just plug those two numbers in. So we had the negative 8.75 as the sum of squared errors shared between x and y, and the 37.5 as the sum of squared errors for x. So the ratio of those two gives us a negative 0.223. And remember what b represents. B is the slope of the line. So that's telling us for a unit change in x, how much does y change? Or in this case, for each additional absence that a student has, we would expect their average to go down by 0.233 grade points. Or you can imagine scaling this. For example, if the student had 4 absences, their grade would go down almost by a full letter grade, from an A to a B to a C, etc. And we can use this slope to determine our intercept. So alpha equals the mean of y minus b times the mean of x. These are numbers that we've already calculated. We knew that the mean of y was 2.85. That was our average GPA. We knew that the mean of x was 3.5. That was the average number of absences. And we now know that the slope is negative 0.233. So let's just throw it in our our equation here and solve for alpha, and you can see that when we do the calculation, we get an alpha of 3.667. Now that's telling us that if someone had 0 absences, remember this is the intercept of the line, and so the intercept of the line can be interpreted as the value of y when x equals 0. So if x is the number of absences, when someone has 0 absences, we would expect their grade point average to be about a 3.667. Perfect. Excellent. Now we can use some of what we know already too to develop a measure of statistical significance. We can calculate a t-statistic for r, for example, using the following formula, where t is equal to r times the square root of n minus 2 divided by 1 minus r squared. Now we have all these numbers already, and so we can just solve it. We put our r in, we put our n, which was 6 minus 2, and then we have 1 minus our r squared value. And let's go ahead and do the calculation. And you can see here that we get a t-statistic at the end of this calculation of negative 3.2497. Or remember that t is an absolute value calculation. So as a result, let's just look at the absolute value of t, the 3.2497. And we just go back to a t-table and look it up. We have, to get degrees of freedom, we have n minus 2, we have 6 observations minus 2, we have 4 degrees of freedom. You can see here on the table where we have 4 degrees of freedom, we're looking for the critical value of t that our calculations exceeded. So our 3.24, let's call it 3.25. We're higher than the 1.5, higher than the 2.1, higher than the 2.7. We're not higher than the 3.7. So the 2.7 was, alpha was 0.05, or we're 95% confident. So we're more than 95% confident we can reject the null hypothesis when we claim that there's a relationship between absences and grade point average. All right, so we can write out the predictive model now as being grade point average equaling 3.667. Remember that was our intercept, right? The value of y when x equals 0, plus absences, the number of absences, that's our vector of x's, times the slope. And we can recall our confidence, and we can now go back and think about our hypotheses. So we can come up with a statement that might say something like this. We can be more than 95% confident that we can reject the null hypothesis when we claim that there's a relationship between absences and grade point average. Moreover, we know that our model, given our r squared, tells us that 72.5% of the variation in a student's grade point average can be explained if we know the number of absences that they have. Finally, we can look at some of these other features here in the model. We can say for each additional absence, we would expect a student's grade point average to go down by 0.233 of a grade point. And we can even use this model to predict a grade point average for students. So let's say hypothetically, we randomly observed a student who had 5 absences. We can put the 5 in the equation for the variable absences and solve it. So we have 3.66 plus 5 times negative 0.233, and we would predict now that that particular student would have a grade point average of 2.5. That's the real power of this type of modeling, is now we can do some predictive things. So we can make a guess about an unobserved observation given our model. Finally, what we can do is we can look at graphing the relationship. And to graph the relationship, of course, you should have a title, and you should have margin titles, and a source. What you do to start off, having set it up, you put it on the scale with the absences and the grade point average. Let's put a coordinate point everywhere we have an observation. So our first observation, we have a GPA of 3.5. That's our y-axis. We have 0 absences. So let's put a point at 0 and 3.5. And let's do that for all of the points. So all the way through, where the absences was 6 and the GPA was 1.6. And that'll give us all the dots. Now we also know other pieces of information. So we know the intercept. We know the point where the line crosses the y-axis. Where y equals 0, we know that the intercept is 3.67. So that's a point on our line. Another point on our line is the centroid. That was the intersection of the mean of x and the mean of y. So that was our mean of x was 3.5, our mean of y was 2.85. So by that rule, our line, and it's a straight line, has to pass through both the intercept and the centroid, so that produces our line. Fantastic. That's a lot of coverage here. Way to go. Now what you can do is you can practice this, and you can do some bivariate regressions in your favorite software package, SPSS or Stata. And as we go back and we think about our hypothesis classification template, what we've done here is we've done what's called ordinary least squares regression. And it's called least squares because we're reducing the amount of squared error we're making when we plot that line. And it's appropriate when we have interval/ratio independent variables and interval/ratio dependent variables. It's a terrific way for us to make predictions, and it's highly informative. So if you recall back to when we were talking about looking at relationships in terms of Kramer's V, and chi-square, there was only so much we could say about a relationship. Now we can talk about the direction in terms of, positive or negative. We can talk about how much of a change each unit of X is producing in Y. We can start predicting unobserved values, etc. So now we have a really powerful tool, the ordinary least squares regression. And it fills one of our boxes in our hypothesis classification template. Great. So just to remind you guys what we've covered, we talked about what linear prediction is. We looked at the building blocks, which was covariance and standard deviation. We calculated Pearson's R and R squared. We walked through the calculations. We discussed statistical significance, degree, and form with bivariate regression. We built a predictive model, and we built a graphic looking at the relationship. Great job, guys. We'll talk to you soon.